Textile manufacturing is a major industry. It is based on the conversion of fiber into yarn, yarn into fabric. These are then dyed or printed, fabricated into clothes. Different types of fiber are used to produce yarn. Cotton remains the most important natural fiber, so is treated in depth. There are many variable processes available at the spinning and fabric forming stages coupled with the complexities of the finishing and coloration processes to the production of a wide ranges of products. There remains a large industry that uses hand techniques to achieve the same results. Processing of cotton. Cotton is the world's most important natural fiber. In the year 2007, the global yield was 25 million tons from 35 million hectares cultivated in more than 50 countries. There are 6 stages: cultivating and harvesting, preparatory processes, spinning, weaving or knitting, finishing, marketing. Cultivating and harvesting cotton is grown anywhere with long, hot dry summers with plenty of sunshine and low humidity. Indian cotton, Gossypium arboreum, is finer but the staple is only suitable for hand processing. American cotton, Gossypium hirsutum, produces the longer staple needed for machine production. Planting is from September to mid-November and the crop is harvested between March and June. The cotton bolls are harvested by stripper harvesters and spindle pickers, that remove the entire boll from the plant. The cotton boll is the seed pod of the cotton plant. Attached to each of the thousands of seeds are fibers about 2.5 centimeters long. Ginning. The seed cotton goes into a cotton gin. The cotton gin separates seeds and removes the trash from the fiber. In a saw gin, circular saws grab the fiber and pull it through a grating that is too narrow for the seeds to pass. A roller gin is used with longer staple cotton. Here a lever roller captures the cotton. A knife blade, set close to the roller, detaches the seeds by drawing them through teeth and circular saws and revolving brushes which clean them away. The ginned cotton fiber, known as lint, is then compressed into bales which are about 1.5 m tall and weigh almost 220 kilograms. Only 33% of the crop is usable lint. Commercial cotton is priced by quality, and that broadly relates to the average length of the staple, and the variety of the plant. Longer staple cotton is called Egyptian, medium staple is called American upland and short staple is called Indian. The cotton seed is pressed into a cooking oil. The husks and meal are processed into animal feed, and the stems into paper. Preparatory processes, preparation of yarn ginning, bale making and transportation is done in the country of origin. Opening and cleaning. Cotton mills get the cotton shipped to them in large, 500-pound bales. When the cotton comes out of a bale, it is all packed together and still contains vegetable matter. The bale is broken open using a machine with large spikes. It is called an opener. In order to fluff up the cotton and remove the vegetable matter, the cotton is sent through a picker, or similar machines. The cotton is fed into a machine known as a picker, and gets beaten with a beater bar in order to loosen it up. It is fed through various rollers, which serve to remove the vegetable matter. The cotton, aided by fans, then collects on a screen and gets fed through more rollers till it emerges as a continuous soft fleecy sheet, known as a lap. Blending. Mixing and scutching. Scutching refers to the process of cleaning cotton of its seeds and other impurities. The first scutching machine was invented in 1797, but did not come into further mainstream use until after 1808 or 1809, when it was introduced and used in Manchester, England. By 1816, it had become generally adopted. The scutching machine worked by passing the cotton through a pair of rollers, and then striking it with iron or steel bars called beater bars or beaters. The beaters, which turn very quickly, strike the cotton hard and knock the seeds out. This process is done over a series of parallel bars so as to allow the seeds to fall through. At the same time, air is blown across the bars, which carries the cotton into a cotton chamber. Carding. Carding, the fibers are separated and then assembled into a loose strand at the conclusion of this stage. The cotton comes off of the picking machine in laps, and is then taken to carding machines. The carders line up the fibers nicely to make them easier to spin. The carding machine consists mainly of one big roller with smaller ones surrounding it. All of the rollers are covered in small teeth, and as the cotton progresses further on the teeth get finer. The cotton leaves the carding machine in the form of a sliver. A large rope of fibers. Note: in a wider sense, carding can refer to these four processes: willowing, loosening the fibers; lapping, removing the dust to create a flat sheet or lap of cotton; carding, combing the tangled lap into a thick rope of 1/2 inch in diameter, a sliver; and drawing, where a drawing frame combines four slivers into one, repeated for increased quality. Combing is optional, but is used to remove the shorter fibers, creating a stronger yarn. Drawing, the fibers are straightened. Several slivers are combined. Each sliver will have thin and thick spots, and by combining several slivers together a more consistent size can be reached. Since combining several slivers produces a very thick rope of cotton fibers, directly after being combined the slivers are separated into rovings. These rovings are then what are used in the spinning process. Generally speaking, for machine processing, a roving is about the width of a pencil. Drawing frame draws the strand out, slubbing frame adds twist, and winds onto bobbins. Intermediate frames are used to repeat the slubbing process to produce a finer yarn. Roving frames reduces to a finer thread, gives more twist, makes more regular and even in thickness, and winds onto a smaller tube. Spinning, yarn manufacture equals spinning. Most spinning today is done using break or open-end spinning. This is a technique where the staples are blown by air into a rotating drum, where they attach themselves to the tail of formed yarn that is continually being drawn out of the chamber. Other methods of break spinning use needles and electrostatic forces. This method has replaced the older methods of ring and mule spinning. It is also as easily adapted for artificial fibers. The spinning machines takes the roving, thins it and twists it, creating yarn which it winds onto a bobbin. In mule spinning, the roving is pulled off a bobbin and fed through some rollers, which are feeding at several different speeds. This thins the roving at a consistent rate. If the roving was not a consistent size, then this step could cause a break in the yarn, or could jam the machine. The yarn is twisted through the spinning of the bobbin as the carriage moves out, and is rolled onto a cylinder called a spindle, which then produces a cone-shaped bundle of fibers known as a cop, as the carriage returns. Mule spinning produces a finer thread than the less skilled ring spinning. The mule was an intermittent process, as the frame advanced and returned a distance of 5 ft. It was the descendant of 1779 Crompton device. It produces a softer, less twisted thread that was favored for fines and for weft. The ring was a descendant of the Arkwright water frame 1769. It was a continuous process, the yarn was coarser, had a greater twist and was stronger, so was suited to be warp. Ring spinning is slow due to the distance the thread must pass around the ring. Other methods have been introduced. Sewing thread was made of several threads twisted together, or doubled. Checking. This is the process where each of the bobbins is rewound to give a tighter bobbin. Folding and twisting. Plying is done by pulling yarn from two or more bobbins and twisting it together, in the opposite direction that in which it was spun. Depending on the weight desired, the cotton may or may not be plied, and the number of strands twisted together varies. Gassing. Gassing is the process of passing yarn, as distinct from fabric, very rapidly through a series of Bunsen gas flames in a gassing frame, in order to burn off the projecting fibers and make the thread round and smooth and also brighter. Only the better qualities of yarn are gassed, such as that used for voiles, poplins, Venetians, gabardines, many Egyptian qualities, etc. There is a loss of weight in gassing, which varies about 5 to 8%, so that if a 2/60s yarn is required, 2/56s would be used. The gassed yarn is darker in shade afterwards, but should not be scorched. Measurements. Cotton counts, the number of pieces of thread, 840 yards long needed to make up 1 pound weight. 10 count cotton means that 10 x 840 yard weighs 1 pound. This is coarser than 40 count cotton where 40 x 840 yards are needed. In the United Kingdom, counts to 40s are coarse, 40 to 80 is a medium count and above 80 is a fine count. In the United States 1 to 20 are coarse counts. Hank, a length of 7 lees or 840 yards, thread, a length of 54 inches, bundle, usually 10 pounds, lee, a length of 80 threads or 120 yards, denier. This is an alternative method. It is defined as a number that is equivalent to the weight in grams of 9,000 m of a single yarn. 15 denier is finer than 30 denier. Tex is the weight in grams of 1 kilometer of yarn. The worsted hank is only 560 yards. Weaving fabric manufacture equals, the weaving process uses a loom. The lengthway threads are known as the warp, and the crossway threads are known as the weft. The warp, which must be strong, needs to be presented to loom on a warp beam. The weft passes across the loom in a shuttle that carries the yarn on a PIRN. These PIRNs are automatically changed by the loom. Thus, the yarn needs to be wrapped onto a beam, and onto PIRNs before weaving can commence. Winding. After being spun and plied, the cotton thread is taken to a warping room where the winding machine takes the required length of yarn and winds it onto warpers' bobbins. Warping or beaming. Racks of bobbins are set up to hold the thread while it is rolled onto the warp bar of a loom. Because the thread is fine, often 3 of these would be combined to get the desired thread count. Sizing. Slasher sizing machine needed for strengthening the warp by adding starch to reduce breakage of the yarns. Drawing in, looming. The process of drawing each end of the warp separately through the dents of the reed and the eyes of the heels, in the order indicated by the draft. PIRN winding frame was used to transfer the weft from cheeses of yarn onto the PIRNs that would fit into the shuttle. Weaving. At this point, the thread is woven. Depending on the era, one person could manage anywhere from 3 to 100 machines. In the mid-19th century, 4 was the standard number. A skilled weaver in 1925 would run 6 Lancashire looms. As time progressed, new mechanisms were added that stopped the loom any time something went wrong. The mechanisms checked for such things as a broken warp thread, broken weft thread, the shuttle going straight across, and if the shuttle was empty. 40 of these Northrop looms or automatic looms could be operated by one skilled worker. The 3 primary movements of a loom are shedding, picking, and beating up. Shedding, the operation of dividing the warp into 2 lines, so that the shuttle can pass between these lines. There are 2 general kinds of sheds: open and closed. Open shed, the warp threads are moved when the pattern requires it from one line to the other. Closed shed, the warp threads are all placed level in one line after each pick. Picking, the operation of projecting the shuttle from side to side of the loom through the division in the warp threads. This is done by the overpick or underpick motions. The overpick is suitable for quick-running looms, whereas the underpick is best for heavy or slow looms. Beating up, the 3rd primary movement of the loom when making cloth, and is the action of the reed as it drives each pick of weft to the fell of the cloth. The Lancashire loom was the first semi-automatic loom. Jacquard looms and Dobby looms are looms that have sophisticated methods of shedding. They may be separate looms, or mechanisms added to a plain loom. A Northrop loom was fully automatic and was mass-produced between 1909 and the mid-1960s. Modern looms run faster and do not use a shuttle. There are air jet looms, water jet looms and rapier looms. Measurements, ends and picks. Picks refer to the weft, ends refer to the warp. The coarseness of the cloth can be expressed as the number of picks and ends per quarter-inch square, or per inch square. Ends is always written first. For example, heavy domestics are made from coarse yarns, such as 10s to 14s warp and weft, and about 48 ends and 52 picks. Associated job titles: piecer, scavenger, weaver, tackler, draw boy, pner. Issues: when a hand loom was located in the home, children helped with the weaving process from an early age. Piecing needs dexterity, and a child can be as productive as an adult. When weaving moves from the home to the mill, children are often allowed to help their older sisters, and laws have to be made to prevent child labor becoming established. equals knitting fabric manufacture equals. Knitting by machine is done in two different ways. Warp and weft. Weft knitting is similar in method to hand knitting with stitches all connected to each other horizontally. Various weft machines can be configured to produce textiles from a single spool of yarn or multiple spools depending on the size of the machine cylinder. In a warp knit there are many pieces of yarn and there are vertical chains, zigzagged together by crossing the yarn. Cotton, warp knits do not stretch as much as a weft knit, and it is run resistant. A weft knit is not run resistant, but stretches more. This is especially true if spools of spandex are processed from separate spool containers and interwoven through the cylinder with cotton yarn, giving the finished product more flexibility and making it less prone to having a baggy appearance. The average t-shirt is a weft knit. Equals finishing processing of textiles equals, the woven cotton fabric in its loom state, not only contains impurities, including warp size, but requires further treatment in order to develop its full textile potential. Furthermore, it may receive considerable added value by applying one or more finishing processes. Desizing. Depending on the size that has been used, the cloth may be steeped in a dilute acid and then rinsed, or enzymes may be used to break down the size. Scouring. Scouring is a chemical washing process carried out on cotton fabric to remove natural wax and non-fibrous impurities from the fibers and any added soiling or dirt. Scouring is usually carried in iron vessels called kears. The fabric is boiled in an alkali, which forms a soap with free fatty acids. A kear is usually enclosed, so the solution of sodium hydroxide can be boiled under pressure, excluding oxygen which would degrade the cellulose in the fiber. If the appropriate reagents are used, scouring will also remove size from the fabric, although desizing often precedes scouring and is considered to be a separate process known as fabric preparation. Preparation and scouring are prerequisites to most of the other finishing processes. At this stage even the most naturally white cotton fibers are yellowish, and bleaching, the next process, is required. Bleaching. Bleaching improves whiteness by removing natural coloration and remaining trace impurities from the cotton. The degree of bleaching necessary is determined by the required whiteness and absorbency. Cotton being a vegetable fiber will be bleached using an oxidizing agent, such as dilute sodium hypochlorite or dilute hydrogen peroxide. If the fabric is to be dyed a deep shade, then lower levels of bleaching are acceptable, for example. However, for white bed sheetings and medical applications, the highest levels of whiteness and absorbency are essential. Mercerizing. A further possibility is mercerizing, during which the fabric is treated with caustic soda solution to cause swelling of the fibers. This results in improved luster, strength and dye affinity. Cotton is mercerized under tension, and all alkali must be washed out before the tension is released or shrinkage will take place. Mercerizing can take place directly on gray cloth, or after bleaching. Many other chemical treatments may be applied to cotton fabrics to produce low flammability, crease resist and other special effects, but 4 important non-chemical finishing treatments are: singeing. Singeing is designed to burn off the surface fibers from the fabric to produce smoothness. The fabric passes over brushes to raise the fibers, then passes over a plate heated by gas flames. Raising. Another finishing process is raising. During raising, the fabric surface is treated with sharp teeth to lift the surface fibers, thereby imparting hairiness, softness and warmth, as in flannelette. Calendering. Calendering is the third important mechanical process, in which the fabric is passed between heated rollers to generate smooth, polished or embossed effects depending on roller surface properties and relative speeds. Shrinking. Finally, mechanical shrinking, whereby the fabric is forced to shrink width and or lengthwise, creates a fabric in which any residual tendency to shrink after subsequent laundering is minimal. Dyeing. Finally, cotton is an absorbent fiber which responds readily to coloration processes. Dyeing, for instance, is commonly carried out with an anionic direct dye by completely immersing the fabric in an aqueous debath according to a prescribed procedure. For improved fastness to washing, rubbing and light, Other dyes such as vats and reactives are commonly used. These require more complex chemistry during processing and are thus more expensive to apply. Printing. Printing, on the other hand, is the application of color in the form of a paste or ink to the surface of a fabric, in a predetermined pattern. It may be considered as localized dyeing. Printing designs onto already dyed fabric is also possible. Economic, environmental and political consequences of cotton manufacture equals, the growth of cotton is divided into two segments, that is organic and genetically modified. Cotton crop provides livelihood to millions of people, but its production is becoming expensive because of high water consumption, use of expensive pesticides, insecticides and fertilizer. Genetically modified products aim to increase disease resistance and reduce the water required. The organic sector was worth $583 million. Genetically modified cotton, in 2007, occupied 43% of cotton-growing areas. Cotton is farmed intensively and uses large amounts of fertilizer and 25% of the world's insecticides. Native Indian varieties of cotton were rainwater-fed, but modern hybrids used for the mills need irrigation, which spreads pests. The 5% of cotton-bearing land in India uses 55% of all pesticides used in India. The consumption of energy in form of water and electricity is relatively high, especially in processes like washing, desizing, bleaching, rinsing, dyeing, printing, coating and finishing. Processing is time-consuming. The major portion of water in textile industry is used for wet processing of textile. Approximately 25% of energy in the total textile production, like fiber production, spinning, twisting, weaving, knitting, clothing manufacturing etc., is used in dyeing. About 34% of energy is consumed in spinning, 23% in weaving, 38% in chemical wet processing and 5% in miscellaneous processes. Power dominates consumption pattern in spinning and weaving, while thermal energy is the major factor for chemical wet processing. Before mechanization, cotton was harvested manually by farmers in India and by African slaves in America. In 2012, Uzbekistan was a major exporter of cotton and uses manual labor during the harvest. Human rights groups claim that healthcare professionals and children are forced to pick cotton. Processing of other vegetable fibers. Flax equals. Flax is a bast fiber, which means it comes in bundles under the bark of the Linum usitatissimum plant. The plant flowers and is harvested. Retting, breaking, scutching, hackling or combing. It is now treated like cotton. Jute equals. Jute is a bast fiber, which comes from the inner bark of the plants of the Caucherus genus. It is retted like flax, sun-dried and baled. When spinning, a small amount of oil must be added to the fiber. It can be bleached and dyed. It was used for sacks and bags but is now used for the backing for carpets. Jute can be blended with other fibers to make composite fabrics, and work continues in Bangladesh to refine the processes and extend the range of usage possible. In the 1970s, jute cotton composite fabrics were known as jutton fabrics. Hemp equals. Hemp is a bast fiber from the inner bark of Cannabis sativa. It is difficult to bleach. It is used for making cord and rope. Retting, separating, pounding. Other bast fibers equals. These bast fibers can also be used, kenaf, urena, rami, nettle. Other leaf fibers equals. Sisal is the main leaf fiber used. Others are, abaca and henequen. Processing of protein fibers. Wool equals. Wool comes from domesticated sheep. It forms two products, woolens and worsteds. The sheep has two sorts of wool and it is the inner coat that is used. This can be mixed with wool that has been recovered from rags. Shoddy is the term for recovered wool that is not matted, while mungo comes from felted wool. Extract is recovered chemically from mixed cotton-wool fabrics. The fleece is cut in one piece from the sheep. This is then skirted to remove the soiled wool, and baled. It is graded into long wool where the fibers can be up to 15 in, but anything over 2.5 inches is suitable for combing into worsteds. fibers less than that form short wool and are described as clothing or carding wool. At the mill the wool is scoured in a detergent to remove grease and impurities. This is done mechanically in the opening machine. Vegetable matter can be removed chemically using sulfuric acid. Washing uses a solution of soap and sodium carbonate. The wool is oiled before carding or combing. Woolens use oils from the worsted combs, mungo and shoddy and new short wool. Worsteds. Combing, oiled slivers are wound into laps, and placed in the circular comber. The worsted yarn gathers together to form a top. The shorter fibers or oils remain behind and are removed with a knife. Angora. Silk equals, the processes in silk production are similar to those of cotton but take account that reeled silk is a continuous fiber. The terms used are different. Opening bales. Assorting skeins, where silk is sorted by color, size and quality. Scouring, where the silk is washed in water of 40 degrees for 12 hours to remove the natural gum. Drying, either by steam heating or centrifuge. Softening, by rubbing to remove any remaining hard spots. Silk throwing. The skeins are placed on a reel in a frame with many others. The silk is wound onto spools or bobbins. Doubling and twisting. The silk is far too fine to be woven, so now it is doubled and twisted to make the warp, known as organzine in the weft, known as tram. In organzine each single is given a few twists per inch, and combined with several other singles counter-twisted hard at 10 to 14 TPI. In tram the two singles are doubled with each other with a light twist, 3 to 6 TPI. Sewing thread is 2 tram threads, hard-twisted, and machine twist is made of 3 hard-twisted tram threads. Tram for the crepe process is twisted at up to 80 TPI to make it kick up. Stretching. The thread is tested for consistent size. Any uneven thickness is stretched out. The resulting thread is reeled into containing 500 yards to 2500 yards. The skeins are about 50 inches in loop length. Dyeing, the skeins are scoured again, and discoloration removed with a sulfur process. This weakens the silk. The skeins are now tinted or dyed. They are dried and rewound onto bobbins, spools and skeins. Looming, and the weaving process on power looms is the same as with cotton. Weaving. The organzine is now warped. This is a similar process to in cotton. Firstly, 30 threads or so are wound onto a warping reel, and then using the warping reels, the threads are beamed. A thick layer of paper is laid between each layer on the beam to stop entangling. Processing of synthetic fibers. Discussion of types of synthetic fibers. Synthetic fibers are the result of extensive development by scientists to improve upon the naturally occurring animal and plant fibers. In general, synthetic fibers are created by forcing, or extruding, fiber-forming materials through holes into the air, thus forming a thread. Before synthetic fibers were developed, cellulose fibers were made from natural cellulose, which comes from plants. The first artificial fiber, known as art silk from 1799 onwards, became known as viscose around 1894, and finally rayon in 1924. A similar product known as cellulose acetate was discovered in 1865. Rayon and acetate are both artificial fibers, but not truly synthetic, being made from wood. Although these artificial fibers were discovered in the mid-19th century, successful modern manufacture began much later in the 1930s. Nylon, the first synthetic fiber, made its debut in the United States as a replacement for silk, and was used for parachutes and other military uses. The techniques used to process these fibers in yarn are essentially the same as with natural fibers. Modifications have to be made as these fibers are of great length, and have no texture such as the scales in cotton and wool that aid meshing. See also, carding, clothing technology, description of Bangladeshi textile engineering course, cotton mill, cotton spinning machinery, dress friction spinning, fashion design, glossary of textile manufacturing, open-end spinning, spinning wheel, textile design, textile manufacture during the Industrial Revolution, timeline of clothing and textiles technology. References. Bibliography, Barfoot, J.R., The Progress of Cotton, Barfoot series of coloured lithographs of 1840 depicting the cotton manufacturing process, spinning the web, Manchester Libraries, Darton, pages 12, retrieved February 11, 2009, Collier, Anne M., The Handbook of Textiles, Pergamon Press, pages 258, ISBN 0-08-018057-4, Curtis, H. P., Glossary of Textile Terms, Arthur Roberts Black Book, retrieved January 11, 2009, G. Duncan. Hunt, Julian, The Cotton Mills of Oldham, Oldham Education and Leisure, ISBN 0-9002809-46-6 Hills, Richard Leslie, Power from Steam, A History of the Stationary Steam Engine, Cambridge University Press, pages 244, ISBN 0-521-45834-X, retrieved January 2009, Naismith, Joseph, Recent Cotton Mill Construction and Engineering, Recent Cotton Mill Construction and Engineering, ISBN 1-4021-4558-6, retrieved January 11, 2009. Roberts, A.S., Arthur Roberts Engine List, Arthur Roberts Black Book, retrieved January 11, 2009. External links, Cotton Yearbook 1910 Descriptions and Calculations for Purchasing All Cotton Processing Machines. 1921 John Hetherington and Sons Catalogue Descriptions and Illustrations of Principal Machines.